Good morning. So I think we can start this event. And thank you very much indeed for being here. I'm welcome to the European Parliament. I'm really honored to open this important conference on rare earth elements organized in collaboration with the European Chemical Society, EuChemS. Let me begin by warmly greeting our distinguished speakers, especially Professor Peter Ruski, Scientific Chair of the event, and Professor Angela Agostiano, President of EuChemS, and my friend Nicola Armaroli, of course. It is a pleasure to host you here today. EuChemS is a vital voice for chemistry in Europe. It represents chemical societies and researchers from across the continent and plays a crucial role in advancing scientific knowledge that we need a lot in this period of fake news, promoting sustainability and supporting evidence-based policy making. And this is also a point. And through its work, EuChemS fosters collaboration between science and policy to address critical global challenges such as climate change, resource scarcity, and energy transition. Today, we turn our focus to rare earth elements, materials that are indispensable to the green and digital transformation. They are at the heart of many key technologies, from smartphones and electric vehicles to wind turbines, medical devices, and of course, batteries. Yet, as all you know, their sourcing and use raise major environmental, economic, and geopolitical concerns. In times of global instability, the EU strategic autonomy hinges on reduction of our external dependencies, especially in sectors as sensitive as raw materials. But our response must not only be industrial or defensive, it must be forward-looking and sustainable. That is why innovation, especially in recycling, process efficiency, and circular economy strategy is essential. Improving our capacity to recover valuable materials means we not only reduce dependency, but also alleviate pressure on our planet. I am very much looking forward to the insights from today's panel. Your expertise will guide us in shaping responsible, science-based policies that match the urgency of our challenges. And now I'm delighted to pass the floor to Professor Angela Agostiano, President of EuChemS. Thank you.
Thank you, Annalise. Good morning, everybody, and thank you for joining today for this important event linked to a topic that I would like to say is very timely for our day, that is on the rare earth elements. But let me first extend my deeply and sincere thanks to Annalisa Corrado that hosts this event, that is a member of the European Parliament, and to Nicola Armaroli, who is the chair of the task group of the EuChemS on circular economy, who is in charge of the program of today's events. And to the end, I would like to thank Nineta Rasteli, the EuChemS Secretary General, for organizing the discussion, this important discussion. I don't see him here yet, but I think that is arriving also David Cole Hamilton, that is the past president of EuChemS and the initiator of the EuChemS Periodic Table, who highlights the sustainability and availability of chemical elements. We are honored of his presence. He's on his way, and we can wait for him to have his contribute again. Now, I would like to just briefly introduce my organization, the EuChemS Chemical Society. Who we are. EuChemS is a sovereign national organization represents over 150,000 chemists through 50 member organizations across 36 countries in Europe. So we are a community that embodies the essence of European collaboration in science, advancing excellence in research, education, and innovation. Our members come from both academia and industry, so more than a network, we believe that our organization, EuChemS, speaks with a unique voice and is a unique example of science united by a shared mission to promote excellence for the benefit of society. We have key messages to leave to you. The first one is that science and chemistry in particular have no national boundaries. EuChemS provides a platform for collaboration that is not constrained by political division. We are all aware that the best breakthrough and the answer to the challenge of our society cannot be made in isolation. And EuChemS can ensure that knowledge flow freely, innovation are shared, and research is accelerated in Europe. Our strength is in the unit because we put together some of Europe's brightest minds to contribute to solving a global challenge that no single country can tackle alone. We are all aware that a fragmented scientific community is not able to deal with global competitiveness, and we very much are responsible for future generation. EuChemS is very much committed to nurturing young scientists by offering opportunities for networking, and policy engagement. Another task of our organization is become a bridge to constitute and solve the gap between science and policy, providing policymakers with scientific advice to shape regulation on crucial issues like green chemistry, pharmaceutical, and resource management. Of course, we advocate for evidence-based decision, and EuChemS in this way wants to influence policies for long-term benefit more than for short-term interests. Today, we are focused on rare earth elements. That is a central theme for the future of Europe, above all in advancing green energy and digital innovation. These materials are essential, and chemistry lies in the core of ensuring their sustainability, secure, and ethical access. Whether through developing new recycling techniques, improving extraction processes, or creating sustainable supply chains, chemistry offers both insight and solution, and is a key to strengthening Europe's autonomy, resilience, and sustainability. So we look at this workshop just to meet the interest of science and policy, and we are sure that we all will learn from everybody, and I wish that this workshop will be very successful. Thank you again. And now I pass the floor to Peter. Yeah, I always I have a problem with the pronunciation. Peter Roski, who will chair the scientific part of this workshop. Please, Peter.
Yeah, thank you very much. Giving me the opportunity to present rare earth in research and technology application. I'm very grateful that we can present this workshop here. So I'm grateful for Nelly Zaccarado to make this possible. For the EuChemS, represented by the president, Professor Agostino, and also by Nicola Amaroli, who is the chair of this wonderful event. In terms of science, rare earths, when I started my career, were basically neglected, and we'll see they are somewhere in the very bottom of the periodic chart. And even if I ask my colleagues if they know the names by heart, they don't know. And so they had been forgotten for quite a long time. And then when in 2010, when it was realized that the supply of rare earths can be used as kind of pressure in economy, it was realized that rare earths are really essential for our high-tech society. For me personally, it was nice coming from somewhere making suddenly high-tech materials, and which boosted my funding. And nowadays, we've seen that in the newspaper, there's a tremendous conflict between China and the US in terms of tariffs. And the export and supply of rare earth is a key point. And this does not surprise us. The European community already defined these elements as critical elements. And we'll see how today a lot of the application of these elements. And so it's a bit of an odd story. We will hear that maybe in one of the lectures. Rare earths themselves are not rare. This is a traditional name. So the natural distribution, what we see is the blue elements. They are medium common. So this is the important point. And why are they so important? And what is the key point here? So they are used in many really high-tech application for our sustainable future. So they are permanent magnets, which are needed in any, like electromotors, modern windmills. They're needed in luminescence, like LEDs in medicine and as catalyst. So this is, these are the major applications, and we need them for our today's society. And this is the problem we face in terms of critical material. So in terms of mining, this was totally dominated by China in 2010. That has changed a little bit. But refining, that what we will also hear today, is a problem because refining realizes that there is waste produced, and this is still dominated by one or two countries. And so this makes the supply chain difficult. What we see here is a mine in China. This is the largest rare earth deposit. But there are also other places in the world, like Australia, where there are a huge amount of rare earth. But in Australia, the rare earths are rarely refined. This is done usually in Malaysia. And that's what we see here. This is a typical extraction plant. And the problem is, since these elements are very similar, the extraction is a high-tech process to get them really separated. And so this is what I found for the European community. This is where the supply comes. It's from 2022, as you realize, from the wet part. The supply from Russia has changed. However, there's basically no supply within the European community. And so this is why European community defined this material as critical raw materials. And this is why one reason why we talk today about these elements. And we have today a wonderful program where we address all these problems I showed in the introduction. It goes from extraction, recycling, policies, optical, magnetic properties, and catalysis. So we cover today scientifically the whole field of application, but also extraction, recycling, and policy. And I'm looking very forward to this program. I'm happy that all the speakers accepted to participate today and to give us a more detailed insight into the field. I just gave a brief overview. And with that, I hand over to Nicola for the first lecture. Nicola Amaroli is coming from Italy. He's coming from the National Research Council in Bologna, and we will hear now a lecture about the foundations of rare earths. So, Nicola, I'm looking forward to your lecture.
Just a few words to thank also my colleague Giorgio Gori, that is here for the first part of our meeting from the Italian delegation of Partito Democratico. He's also a full member in ITRE, in the committee ITRE. And I forgot to say that I'm in ENVI, ITRE, and also Agri. And so we are at your disposal. We also have some assistant of other colleagues. And so just a quick information about this.
Good morning. Thank you, Annalisa, Angela, and Peter for this introduction. My homework today is to explain what is our periodic table. Actually, we have already a periodic table, and it's very well known. It's full of information, chemical, physical. So one may wonder why we need a new periodic table. We already have one. And everything started out in 2019 during the International Year of the Periodic Table, when EuChemS decided to spread another type of table, this one, that had been already published in the 1970s in the United States, but it went essentially forgotten. And we decided to kind of resurrect it and to integrate it, to update it, and to spread it around. And what is the meaning of this table? Each element is characterized by size. So the larger the size of the element, the more relatively abundant is that element in the compared to the others. And the other information is the color. The color goes from red to green, all the way to green. And red means that they are elements for which we are in danger of being in lack of it within the present century. And the green ones are those for which we don't have any problems about availability probably for centuries. And then we have the intermediate obvious color of orange and yellow. So the table, when we made it in 2019, we decided that it was to be a living document, okay? So to be updated by a scientific discussion over the years. And this is what we made. So we decided to discuss element by element, those more critical, those more important at the moment. And we started from carbon in 2021. And then we moved on to lithium, 2022. And then 2 years ago, we discussed both nitrogen and phosphorus. And the phosphorus meeting was right here at the European Parliament. So why nitrogen and phosphorus? Because there is a problem of nitrogen and phosphorus overuse in our planet, and their use is beyond the so-called boundaries, the safe boundaries of our planet. So the biogeochemical cycles of nitrogen and phosphorus are out of control due to intense fertilization and intense use. And this has been described by many institutions like the Stockholm Resilience Center here. So based on this discussion, I briefly mentioned it, we made two other versions, and this is the latest version published in 2023. And what did we change? We highlighted more the sustainability. We added one question on top of it. Is it sustainable, a given element? And we highlighted this sustainability with a new color, which is deep red, which indicates the overuse of that element and the problem provided to human civilization by the overuse. So we changed the color compared to the first version from full green. Actually, carbon is an element which is plentiful on this planet. But if we look carefully, we obtain carbon primarily from hydrocarbons, so it's black, and we have been making wars for the control of hydrocarbons for over 70 years. So carbon deserves the black color and also deserves the red color because its overuse is creating a generation of huge amounts of carbon dioxide which are discharged in the atmosphere and create climate change. And then we also changed the color of lithium from yellow to orange due to increased use. And this is a very hot topic, as you know. And we added also the deep red to nitrogen and phosphorus compared to the previous version for the reasons I mentioned before. Today, we are going to talk about the rare earth elements, which are 17 metals. Actually, they are 16 because one promethium is essentially synthetic, because it is highly unstable. So we have 14 lanthanoides and plus scandium and yttrium. They are split in heavy and and light, and the heavy are typically more expensive and more rare. As chemists, we know that rare elements are neither rare nor earth. These are traditional names which have been indicated in the 19th century, and there are historical reasons for that, which I don't have time to discuss. And from the chemical point of view, it is very important to highlight for us that they have very, very similar chemical properties and behavior. And this, the consequence of this was it took over 1 century to separate them all and to individuate them all. So they have outstanding properties, as already mentioned by Peter, magnetic, luminescent, and optical, which are given by the progressive filling of the f orbitals of these elements, which provide them these unique properties. The rare earth elements are critical materials for EU. We know that there is a continuously updated list of critical materials for our economy, which are important for our economy, but Europe doesn't control the supply chain of these materials. This is the meaning of critical. And there are 34 of them. And one of these entries out of 34 is the whole family of rare earths. And of the 34, there are 17 which are strategic. Strategic means that they are key for defense and for green and digital transition. Well, rare earths are, all of them are critical, and part of them are even strategic. And some are strategic, typically the heavy ones. The criticality, let's just give you an example. Let's take neodymium iron boron magnets, which are very widespread. And the colors, the different colors represent countries, and the gray part represent different parts of the value chain from mining all the way to manufacturing. And you see that there is a dominance of red. Red is China. So China controls the majority of the mineral extraction, but also by far the majority of all the processes that make these kind of magnets available. Here, of course, the key element is neodymium. So China is dominant all across the supply chain. So rare earths are essential for several applications. They are used both in a metallic state or in a ionic state, let's say, and for different applications like catalysis or permanent magnets. We have rare earths in our pockets. There are up to 8 rare earths in our smartphones. They provide specific properties. If they vibrate, it's due to the presence of some rare earths. The color of the screen is provided sometimes by several rare earths and other functions. Availability, 80% of known resources, according to the US Geological Surveys, are concentrated just in 3 countries. So they are very concentrated resource at present, given the present knowledge. And China dominates this, and the Inner Mongolia mines have been already cited by Peter. What about the energy transition and rare earths? They are very important, and I just pick one example for wind energy. This is an interesting picture provided by the JRC, the European Research Center. There are on the left several critical materials from red all the way to green. The red spot is heavy, is rare earth elements, both heavy and light. And as you see in the Sankey diagram, there is a lot of red going to wind energy. And they use it intensive, and 5 of them are typically used in permanent magnets, and the amount used is very high. The EuChemS Periodic Table aims at promoting a circular perspective, because as chemists we know that even the green elements are not available in infinite supply. All of them are finite supply. So we have to be very careful in using them, and you have to provide the circularity of their use, because fortunately it's not like hydrocarbons, which are extracted, burnt, and then trashed in the atmosphere. Mineral resources can be extracted and recycled. So that's very important, and chemistry is key in promoting this circular perspective. The recycling rate of metals for Europe, this is these are old data, but I didn't find more recent ones, but I don't think that the situation has changed substantially. For Europe, you see only 2 blue spots for higher recycling, above 50%, which is silver and lead. And for the others, the rate of recycling in Europe is still too low, especially for rare earths, which are at the bottom of this table. You see that the percentage of recycling is really, really low. Well, our table made an impact. It was reported in a report for of the European Environmental Agency on circular economy. Several international media talked about our table. The Guardian published it. The New York Times published our table. The BBC discussed our table. Our table now is present in textbooks in secondary schools, like in Italy, we have them. And also a stamp was made out of with our table, which is quite surprising to us. This has been done by North Macedonia. And the scientific discussion of EuChemS on elements will continue. We have already spotted other elements which deserve discussion, and I look forward to having this discussion in the next following years. And during this year, we realized a very important point. Our table is a call for international cooperation. Why? The elements we discussed, like carbon, rare earths, lithium, phosphorus, are concentrated in the spot that I reported there. They are present also in other places on Earth, but they are specifically concentrated in these spots. And this is true for any elements you can pick. So mineral resources are typically concentrated. So every country needs everything, but every country does not have everything. So what is the way out of it? The only possibility is international cooperation and sharing of these resources. Otherwise, we will not make any transition, green transition, digital transition, or even any other kind of progress we want to implement. Finally, I would like to thank the people that contributed to this endeavor over the years, particularly the former president, David Cole-Hamilton, who just joined us, and former President Flores Rugis and current President Angela Agostiano, and all the other colleagues I reported here. And we also invite external experts for each element. These are the experts we have invited over the years for nitrogen, phosphorus, and now for rare earth, we have Peter Roeski, which I thank very much. This is my last year as chair of this task group of EuChemS, because my term as member of the European Chemical Society in the board is terminating at the end of this year, and I look forward to having the next chair and the person who will continue this work. And I thank you all very much again. Thank you for your attention.
Okay, thanks a lot for this really nice overview. And we have the discussion at the end, so I hand over to the next speaker. So presentation is on. Okay, so this is Andrea Dini, also from the Italian National Research Council from Pisa. And you already see we were here now about rare earth extractions. And so this is addressing the first part of the hot topics that were given in the introduction. So Andrea, the stage is yours.
Thank you. And thank you for the invitation. I'm very honored to stay here with all these colleagues, chemists. Chemists are like geologists. No, we were, in the past at least, we were so overcharged of responsibility about the environment, but geologists and chemists, I believe, they find solution, not create problems. So it's nice to be here. So I will show you some information about rare earth elements throughout the world, and something also about Europe. And okay. So this is a beautiful picture of Milky Way, hydrogen, helium, but something more, of course. But the cosmos is made of mostly of hydrogen and helium. And we are very, very lucky to stay on the Earth, because the Earth has a geodynamic process, has water, has a lot of ingredients that allow allowed in 4.5 billion years, creating the Earth crust, the continental crust and the oceanic crust. Producing this kind of enrichment of many elements, many metals, all the elements that we use every day since at least 8,000 years. So we live on a lucky planet, and we had to know which kind of metals are in our rocks. The geologists do this job, and in this map you see a general view of the rare earth element deposits in the world. You see that rare earth elements are not so rare. We have a lot of deposits. Some of these deposits in the map are not developed yet, but they will be developed in the near future. So I believe that the supply of these materials is not a real problem. Maybe the control of these metals could be a problem, like oil and gas in the past. So, and the role of scientists and also European Union should be this, to maintain an equilibrium between the powers and for the management of these metals. So China is the leader, of course, we know, but is almost a monopolistic leader, because China developed the value chain from the extraction to the final product on the market. So China projected in the past a well-organized value chain. In Europe, we are discussing about deposits of rare earth elements, but we need to develop this kind of exploration and valorization of these metals in a value chain that include the industrial development of this material. So otherwise, we cannot produce rare earth element and then sell to the next country outside Europe. So in this graph, you see the price of different rare earth elements. There are very cheap rare earth elements like cerium, but there are very expensive metals like terbium, dysprosium, praseodymium, neodymium. So the most important rare earth element on the market. So the variation, okay, we cannot discuss about variation, but of course the bumps are connected to important events in the world, social, economic, and political events. And in this diagram, we see the story of rare earth element production since the beginning of the 20th century. Okay, of course, like many other metals, until the end of the Second World War, the production was really small, like lithium. But after the Second World War, there was an increase in production and in demand, of course. And the first 30 years were dominated by the mountain pass era. So the mountain pass was a big deposits in the United States. These deposits produce bastanysite. Bastanysite is a carbonate, fluorocarbonate mineral of rare earth elements. And then the mountain pass mine around 90s start to decrease production, and the Chinese era start. So you see that until 2013-14, China totally controlled the production of these metals. But then after we recognize the problem of the monopolistic role of China, we start exploration again in many countries in the world, and we start again the production. So now the situation today is much better. So our politics, our activity, research activity, scientific activity was good, and we obtained results all over the world. So now US is again a producer of a rare earth element, and Brazil is becoming probably one of the strongest producer of rare earth element in the world. and many other countries, you see. And in this diagram, is nice to see this because we can discuss on this diagram for 2 or 3 hours if you want. And you have the million tons of resource in the deposits versus the grade, the weight % of rare earth element in the material that is mined in the deposit. So on the upper right part, you see Bayanobo is this huge, is the greatest deposits of rare earth element in China, in Inner Mongolia area. So you see the reserves are 100 million ton of rare earth element oxides. So it's a huge amount, really huge. And the grade is quite high. And then if we go down, you see the South China is on the left, the lower left corner, or the lower right corner, sorry. So South China means the regolite hosted the rare earth element deposits. So the deposits where rare earth elements are adsorbed on clays, in soils, in very thick soils, of course, in very hot and humid climate zone. And South China has these two big deposits. You have Bayanobo, primary bastanizite deposits, and the South China adsorbed rare earth element on clays. The deposits of South China are huge, but the grade is extremely low. So why these deposits are exploited? So Bayanobo, okay, is big and rich, but why South China? Because removing rare earth element from the surface of clays, it's very easy. We don't need to destroy the minerals to break the bonds, the chemical bonds between elements. We just leachate the elements using solution, acidic solution. So in South China, do this. And doing this, they control the market of heavy rare earth elements, so the most pricey elements in the group of rare earth element. So they were lucky. They have this kind of rocks, this kind of regolite, but they were very clever to develop the technology, to develop the science about the extraction from clays. So, just a second, yeah. So you see, this is I'm sorry, is a table with very small fonts, but this is a table of the 30 most important deposits in the world. And it's a list, but you can see later. But at the top, you have Bayanobo, because Bayanobo is the greatest deposits in the world. But then you have Tambrez, I don't know the pronunciation, and South China clays, of course, and then Kvanefjeld in Greenland. So just from this table, you understand the political discussion that polarized the newspapers and the media in the last 2 months. So Greenland is in Europe and contain a lot of deposits of rare earth element, but very important one, because if you look at the right column, you see 3 red boxes. In that red boxes is written that the heavy rare earth element in the Greenland deposits is huge, are very rich in heavy rare earth elements, like the rare earth elements that are produced by the clays in South China. So Greenland has deposits of rare earth element, and in particular, they are very rich in heavy rare earth elements. So these are two important strategic conditions. So Bayanobo, yes, just few pictures. On the right, you see the open pit. Well, probably this is the eastern. There are 2 big open pits, and so this is the eastern one. The mineral that is exploited in Bayanobo is like this. This is one of many types. And the brownish mineral is fluorocarbonate of rare earth elements, bastanezite, but there are many very strange and rare minerals that have been found just in these deposits. So this is Bayanobo, and then a picture from Greenland. This is eudialyte granite from the southern part of Greenland. Also in this case, 26% of the rare earth element in this rock include heavy rare earth element. This is the very important information. And then, yes, South China, the clays, you see there are granites that were weathered through time, and a very thick profile of weathering and alteration, oxidation, produce mobilization of rare earth element and fractionation between heavy and light rare earth element. So this natural process was really important to enrich the soil, the regolite, in the heavy rare earth element. This is the most important thing from these deposits. The problem is this one. The Chinese exploited this kind of deposits by in situ leaching. So they inject fluids, they inject solution, water plus ammonium sulfate, and they desorb rare earth element from the clays and then collect downhill in basins. So you can imagine that it's almost impossible to control the underground path of solution in this area. So a big part of the solution probably will go in the basin at the base of the hill, but other part of the solution can move and can be dispersed in the environment and can produce pollution. And so for this reason, the Chinese community developed a lot of research, scientific research, and they start to exploit these deposits using electrochemical methods. So they inject the fluids, the solution, but then they put cathode and anodes to force the migration of rare earth elements from the injection zone to the collection zone. So this reduce a lot the amount of ammonium sulfate, 1/5 probably, and reduce the environmental impact. So this was a significant improvement. But of course, yes, we need to develop this more and consider that now this kind of deposits, the regolite hosted deposits, have been discovered and are developed in Madagascar, in Myanmar, in many other regions of the subtropical area. So the problem of South China will spread throughout the world. So we have to really have a look on these processes and on this research. So in this one of the last diagrams, you see many stars and many circles, and the red ones are the project, the exploitation project that will produce heavy rare earth elements. So there is a significant amount of heavy rare earth element deposits, but many of them are not ongoing, so they are in development. So most of the heavy rare earth elements today are coming from South China, probably 100%. So Europe did, before the Critical Raw Material Act, did very important projects in the Horizon program. One of these is EURARE. It's a very nice project, full of information. And in this project, many different deposits from Greenland, Sweden, and other areas in Europe have been considered and studied and characterized. And also the treatment of the material has been developed. So these kind of projects were very important then for the Critical Raw Material Act. And you see, we have occurrences of rare earth element deposits in all the countries of Europe, more or less. And during the past few years, new deposits have been discovered. One of these is in Sweden, the Pergeger, I don't know the pronunciation, I'm sorry, is near Kiruna. Kiruna probably you know because it's one of the most famous deposits of iron in the world. Is exploited since 2 millennia probably, and now it's still active. And the company did the exploration and discovered the bluish body to the north of Kiruna deposits, and this body is similar to the Kiruna one. It's magnetite, iron oxide, but it contains an anomalous amount of apatite. Apatite is a calcium phosphate, and the Kiruna apatite has a significant concentration of rare earth elements. So the Sweden company is developing a beautiful project for an industrial plant that will produce phosphate and rare earth element, and they are developing this project just now. So this is a possibility to recover rare earth element from unconventional deposits, not clay, not bastanezite, but from apatite in Sweden. But then there is another approach. In this case, it's impossible to produce a huge amount of a rare earth element, but we can produce a byproduct rare earth element by optimizing the activity of raw ceramic material quarries. So there are many granite quarries all over Europe, also in Italy. This material several times is used for ceramic industry. They separate feldspar and quartz, and they put in waste the iron-rich mineral. But if you look using a microscope inside this waste, you see that there are the greenish, yellowish are sodium feldspar, the bluish is potassium feldspar, and then you see very black crystals of biotite. And biotite is an iron-rich mineral. It's not good for ceramic. But inside the biotite, you have a huge amount of this tiny crystal, yellowish crystal of monazite. Monazite is a rare earth element phosphate. So this material goes in waste. So we can use this waste to produce a byproduct for the diversification of the production area for rare earth element in Europe, not just to become the most important producer of a rare earth element in the world, but just to diversify the activity in Europe. So these are a different approach. So I show you all these things, and okay, I finish here. And if you have questions at the end of the morning, we can. Yeah.
Yes, thanks a lot for this really nice overview over the deposits and how to extract the materials. And now we go on in a logical way. After extraction usage comes recycling. And so we go in circular economy, and I'm happy to introduce Marine. She's from the ETH Zurich and also co-founder of a company called Recover. And the stage is yours. I'm looking forward.
Thank you for the very kind introduction. It's a great honor to be here. I'm going to try to cover in these 15 minutes a very important topic around the recycling of rare earth elements and try to answer this question: how can rare earth recycling be improved and embedded in circular economy principles? Just before touching on that, to understand why circularity is so important, a very short introduction, and these are things that you have heard already and that you will keep hearing throughout the day, but some very important things to know about rare earth elements. Again, not so rare, quite abundant in the earth crust, some of them as abundant as copper, and orders of magnitude more abundant of what we call rare metals like silver and gold. And the key thing to understand is that they're extremely challenging to separate from another. I will touch on this in a second, but most of the main reason for that is that they're commonly found in the stable +3 oxidation state. So I would say similar redox chemistry most of the times. And the only thing that really discriminates them is a really small decrease in ionic gravity with increasing atomic number, as you can see in white on this scheme. And finally, they also behave in very different ways from transition metals, and this is also what grants them their unique magnetic, optical, and luminescence properties. And so they behave like ions with really oxophilic characters and large coordination numbers. Now, as it was very well mentioned before, they're all commonly found in the same natural ores. Here you have bastnasite, and if we talk about them today, it's because there's the so-called vitamins of the industry. So you find them in rather small quantities, sometimes larger quantities, in a wide range of applications and sectors, from the medical sector, defense sector, energy, so on and so forth. And because they have unique properties, they're all used in different applications. You will find neodymium in the magnets, terbium in the luminescence properties. And so if this would be picturing, I would say, like an ideal picture, but one of the main problems when looking at rare earth mining is the so-called balance problem, is that they're all found in the same natural ores, but not in the same quantities. So like the light ones are more abundant and the heavy ones are way less abundant. And for example, if you look at lighting applications, so like all the lamps, energy-saving lamps, which require large quantities of europium and terbium, which are much less concentrated in the ores, this means that you have to process a huge quantity of natural minerals in order to reach the given amounts, which means that you also have to stockpile the other elements that you don't necessarily need in such big quantities. Again, these elements are really the pillars now for both the energy and the digital transition. Here you see examples of the quantities that you have in a small wind turbine or an electric car. And for all these reasons, the International Energy Agency predicts their demand to really skyrocket in the coming years, especially if we want to keep in line with the Paris Agreement. And this really brings about two other major problems. Again, the first one is an environmental one, because they're so challenging to separate from one another and quite found low concentrations in the deposits. Mining 1 ton of rare earth elements will generate 2,000 tons of toxic waste, including 1.4 tons of radioactive waste, as you find in these natural ores, radioactive elements such as uranium and thorium. And then, as it was highlighted before, a very big geopolitical problem. So global rare earth production, almost 70% being controlled by China. And this number really goes way higher to above 90% when you look at the refining, so like the processing, purification, and separation of these elements. And for all these reasons, heavy and light rare earth elements have been classified for many years now as part of the European critical raw material list, because for both their economic importance in very critical sectors, but also their really high supply risk. Now, these are the problems that we're facing: the balance problem, the very large environmental impact of mining, and the supply risks. And most of these problems actually stem from the fact that the rare earth economy is actually a very linear one. From the mining to the final product, this all ends up to waste. And as we've seen before, current recycling rates at the global scale usually fall below 1%. This is the number that we tend to give. It's going a bit higher now, but still very low recycling rates. And so to solve all three of these problems, it would be very interesting to start implementing a more circular economy of rare earth elements in reusing, remanufacturing, and recovering these elements from final products. What is interesting here is that there are two main recycling schemes that have been developed now industrially: the so-called short loop, which basically looks at taking one specific waste stream and try to remanufacture the same type of materials out of this waste stream. And then the so-called long loop recycling, where you take any type of waste stream, secondary source, and try to recover the individual rare earth oxides from that stream. Now, there have been many studies to try to identify economically viable secondary sources of rare earth elements. I would say the largest proportion is actually from industrial waste. So, for example, in bauxite residue, so-called red mud, which comes from the bioproduction of aluminum, phosphogypsum, which is a byproduct of the phosphorus industry, coal ashes, which comes from burning coal, fuel cracking catalysts, from the car industry, and polishing powders from the glass industry contain really large quantities of rare earth elements. Quite an obvious one as well is looking at mining waste, so from like acid mine draining, which also contain large quantities of these elements. And finally, the one that we probably talk the most about nowadays is to actually try to recover rare earth elements from the waste we produce as individuals, so like our electronic waste. And there you have really interesting quantities of rare earth elements in phosphorus applications, so like lightning applications, nickel metal hydride batteries, which were widely used in the past and now transitioning to lithium ion batteries. So they're being a large amount of waste being generated for these batteries, and obviously then magnets, which you find everywhere from hard drives to speakers to electric cars and wind turbines. Now, coming back to the original question, how can recycling be improved and embedded in the circular economy? And my personal opinion on that is that it needs both innovation and policies. And so policies will be discussed in the upcoming talk. So I will focus more on the innovation part and close very shortly on policies. Sorry, this is very small, but this was highlighted before. Rare earth separation has been a chemist's challenge for now over 200 years. And this is why their discovery took more than 100 years. And this was quite interesting now talking about periodic tables, because this was a real brain scratcher for Mendeleev himself when he was trying to develop the first version of the periodic table in 1869, because at that time, actually, not even half of the elements had been properly identified. And so, yeah, we would probably need a full other day to discuss all the different types of separation techniques that have been developed throughout the years, because many things have been tried. And so separation techniques are usually separated in 4 different families. So-called hydrometallurgy, which is like a chemical process. And here you will find like actually how the rare earth elements were originally discovered by fractional crystallization. And then throughout the years, especially with the development of the Manhattan Project, the development of ion chromatography, and then in the 50s, liquid-liquid extraction, which really implemented itself as the now mainly used industrial process for separation of rare earth elements. You also have pyrometallurgy, which usually involves high temperature treatments, electrometallurgy, so like using electrochemistry, as we've seen in the previous talk, and biometallurgy now, which is very interesting from an environmental perspective. So looking at natural proteins and enzymes, which can bioleach or bioabsorb rare earth elements, but these are now not yet being used at an industrial scale. Just to give a few, yes, sorry. Problem with all these separation techniques is that they have been optimized for the separation from natural ores, but as soon as you, in a chemical process, as soon as you start introducing a different input in your process, it might change the entire process as well. And so now the interesting question is that depending on the nature of the secondary source that you're using, how will the separation process be modified all the way from the beneficiation to the chemical extraction and separation of your rare earth elements. Just to give 3 examples of some concrete cases where we are able to recover rare earth elements from. The first one from industrial waste, so from phosphogypsum, which is the main byproduct of the production of phosphoric acid, so by acid treatment of phosphate ores. More about the topic on the really great workshop on the phosphorus element, so the latest EuChemS workshop. And what's really interesting with phosphogypsum is that you find there really high concentrations of all the different rare earth elements. And so there have been, again, many processes that have been studied in the past to see if it could be applicable. And sorry, the table is extremely small, but from this review, I found what was really interesting is in the disadvantages, very often it's actually written that it needs more research and development to be able to be used at an industrial scale, which is not the case today. Moving on to electronic waste, this is what we focus on, especially at Recover, is to recycle rare earth elements such as europium from end-of-life fluorescent lamps, which is an extremely interesting waste stream because it beneficiates from really high collection rates and known physical dismantling. And so now we've developed and patented a process to recover europium with really high selectivity and really high purity in a single separation step. And we're currently working on the industrial development of this process. But there have been many other developments in this field as well. And now the waste that probably gets the most attention these days is actually magnetic scrap, because it represents the larger utilization of rare earth elements in our modern economies, and it's also the share that is expected to increase most in the coming years. And so the recovery of praseodymium, neodymium, and dysprosium. I would say the main challenge regarding magnetic scrap is that current ferrous, so like current magnetic streams, are too diluted for a feasible recovery. So it needs a bit more sorting and separation in the first stage, so like in the waste collection stage. And the fact that these rare earth magnets are found in consumer products, that requires a lot of like physical dismantling from like phones, for example, or computers, which also need to be optimized in order to have a stable waste stream of magnetic scrap. Again, many techniques from hydrometallurgical, parametallurgical that have been developed with their own advantages, disadvantages. I think what is important to highlight here is that on all these different techniques, a lot of life cycle analysis have been conducted, which also really dramatically show the environmental positive impact of recycling magnetic scrap, especially in the short loop process. Now, the good news is that probably since the rare earth crisis in 2011, there have been a lot more investments in Europe, especially to look at the separation of rare earth elements, especially now focusing on magnetic recycling. So you see some examples here of plants that were already established and that focused mostly on short loop recycling of magnetic waste. And now, more recently, there have been 47 strategic projects that have been funded by the European Union under the Critical Raw Material Act, and 5 of them focusing on rare earth elements, all the way from extraction in Sweden to recycling, again, magnetic waste, but now with a much stronger focus on long loop recycling, so to be able to recover pure rare earth oxides from any type of waste stream. I would say, overall, rare earth recycling poses many opportunities and challenges. I would say main opportunity is the increasing feed to meet the increasing demand. If we don't start looking at secondary sources, we see now many mentions of projects like deep sea mining or asteroid mining, which would have dramatic environmental impacts. This also allows us to do more waste valorization, especially looking at e-waste, which is one of the highest growing wastes, especially in Europe. Obviously, positive environmental impact following the UN Sustainable Development Goal number 12 on responsible production. And it also fixes the balance problem because now you're able to recover only the rare earth elements that you need in a given technology. Of course, if this is not currently being done, it's because there are many challenges still to answer. First one being a technological lag. So like most of the separation processes that have been used in the past 100 years have been optimized for the separation from natural ores. And now looking at waste streams, again, with very complex value chains and sorting that needs to be done, these processes have to be optimized. And looking at waste streams and working with waste and recycling in general, this is also valid for plastic recycling. It's really hard for recyclers, given the changing nature of the waste inputs, to have like a stable output quality, which is necessary if you want to have like an economically viable process. And now, and probably the most important challenges of all is actually the economic viability. So how can you produce recycled rare earth elements which can compete with the current very low market prices for the different rare earth oxides? And the good news is that there are many answers to these challenges as well, and some of them can be solved by policies. Again, a very small opening for the following talk, but at the European level, the European Critical Raw Material Act, which has been enacted last year, has some very strong goals to meet by 2030. So global EU needs should be met by 25% from recycling rare earth elements. And now there are also discussions on extended producer responsibility, which could improve collection rates and sorting of the different electronic waste streams containing rare earth elements. And these policies are really critical because they can, again, improve the collection rates, but also like incentivize companies to take, for example, pledges like Apple did to use 100% recycled REEs by 2025, so by this year. So this is why both innovation and policies have to go hand in hand if we want to implement a more circular economy of rare earth elements. Thank you.
Yeah, thanks a lot for this great overview of recycling and also where the problems are in terms of waste treatment. And you gave already a really nice introduction to the next speaker, and we heard already that European Commission did a great job in terms of policy making. And now we hear from Milan Grohl a little bit more detail about these topics. So please.
Thank you, Mr. Chair. My great thanks for a very kind invitation to this event, very focused, very relevant to current situation, but already situation for the last 15 years. So that's nothing new. I'm very thankful to the previous speakers to make my life much easier. And I'm very proud that also with colleague Gabriel Niefel, here we are from the team of the European Commission DG GROW, which is something like the Ministry of Industry at national level. We are actually focusing on the rare earths and magnets in the team. And I'm very proud that you refer to our work, because our team is developing the studies on critical raw materials assessment, foresight studies, which have been mentioned several times, also in-depth analysis. So it's really great to see. So and also we are working on the strategic projects under the Critical Raw Materials Act. So that's something which is in our team. So starting with the Critical Raw Materials Act, this is a game changer in the EU. Is the first legislation which is positive towards the supply or securing supply of raw materials in the EU. What is very important, and I'm also happy that you mentioned that, I think Dr. Dini mentioned that already, we have priorities. For the first time is critical and strategic raw materials. So that's something very important to mention. Rare earths are both. The whole Critical Raw Materials Act is relevant to strategic raw materials. All provisions, all legal provisions are relevant to the strategic raw materials, and rare earths are strategic. So that's very important. There are different objectives of the Act. One is to strengthen the value chains in the EU, and there, or the supply chains for our industry. There we focus on strategic projects. We also promote the exploration programs in the EU member states. That's another block of provisions, and we are doing quite substantial R&D funding from our side. We are spending roughly over 100 million per year under Horizon Europe for raw materials topics, and rare earths played a big role in this funding. So, just that you know, with Gabriel, we are also programming the Horizon topics. So when you see raw materials chapter, that's our chapter. Second, we want to diversify also with the supply from the third countries. There we focus on the strategic partnerships. I will come to that a bit later. We are promoting very much circularity. So thank you very much, Dr. Perrin, to highlight the importance. I will mention a few things there. And we are doing very in-depth monitoring and supply chains assessments. And we also have something new, which is the mitigation of risks. So stockpiling and joint purchasing. So we are going in this direction as well. The act or the regulation concretely came into force last May. So a lot of things have been programmed for this year or last year and this year. A lot of deliveries should come by the end of this year. So hopefully we will manage. So these are 34 critical raw materials and 17 strategic. All rare earths are critical. Magnetic rare earths are strategic. This is roughly a scheme of the whole act. I will not spend too much time on that. There are blocks of provisions on strategic projects, strategic partnerships. I will come to that a bit later. On exploration programs, we are really encouraging member states to invest in exploration, finding new deposits, identify the ones which are good for further development by industry. Then we have circularity provisions and sustainability. I will come to the part of magnets specifically. And we do vast risk monitoring, everything from criticality assessment, stress testing. This is a new thing, early warning system with other countries. We do the foresight and in-depth supply chains analysis. Not everything is public, I must say. Production, we are screening the production projects across the whole EU with member states and directly. And we have provisions also on identifying key market operators. So that's a big monitoring part. And on risk mitigation, I mentioned we are discussing with member states the strategic stocks or stockpiling, and we are building the demand aggregation platform for downstream industry to get better access to raw materials, especially some of the strategic raw materials. We have priorities. We mentioned the critical and strategic, and we have the benchmarks. They are not binding, but it's for the first time that in this area we have something which indicates our ambition, and that's something very important. So for mining, we would like to have at least 10% of domestic production. It looks very low. 10% is nothing, but starting from zero is quite a lot in many cases. Processing capacity, in some cases we are very low. 40% looks very high, but I'm grateful that we still have something in the EU, especially in the area of metallurgy. For recycling, our proposed benchmark has been increased by the co-legislators to 25%, which is extremely ambitious, I must say, because you will see that later, most of the recycling input into manufacturing in the EU is below 1%. So to go from 0 to 25% in 5 years' time, it's quite a challenge. Then we have also one benchmark on diversification of supply. We would like to decrease our dependence on a single producer or importer under 65%. This is also quite ambitious for some materials. This is the map which we produced from the criticality assessment. This is our dependencies, and you see rare earths, China, for heavy rare earths, 100%. This will be hopefully fixed soon with our strategic projects, but we still miss certain value chain stages. So as you see, we are especially in the red parts, we have very high dependence on many materials. So it's not only about China, it's about also other countries. What we are doing at the international level, we are focusing on specific countries. We are not focusing anymore on the regions as such, but we are going country by country, which has some potential and can build stronger links with our industry. So we have 14 partnerships signed. It will slowly, maybe some countries will be added, but we try to develop the roadmaps and work with these countries quite systematically. Just for information, all the slides will be shared, so no need to take pictures or spend time on it. At the EU level, we also mapped the production rare earths. Practically, we had information about, we know the numbers, but we cannot publish because they are not public. The only producer of processed rare earths was in Estonia, but the numbers are not public, as I mentioned. And second, the situation is changing quite quickly. There are no running mining projects yet in the EU. So that's also another conclusion, which also my pre-speaker mentioned already. So that's a quite tragic situation when you see how China from 80s systematically built a strategic production capacities going down from raw materials to processed materials to components and products. It started around 85, if I'm not mistaken, and by 2000, in 2005, they started with the export quota and export duties, which have been ruled out by WTO only in 2015. By that time, our industry has been completely ruined, so in the West. And they are using the export restrictions, especially licensing, until today very effectively and very specifically. So very long track record of of targeted price manipulations on the market and the control of the production. I'm happy that you show the map of the projects around the world. This is the map from roughly 2010-11, when around 100 projects have been announced around the world, and they died within 2-3 years, practically all, except for one, Lynas in Malaysia, so the Australian company Malaysia, which has been directly subsidized by the Japanese government via JOGMEC agency. So that's the only one which survived. Even Mountain Pass died, which was the major production spot in the world, in the United States in the past. And Europe ended up like this. I don't have a map of the deposits, but you've shown there are plenty in the EU. There are many, really many, but we are not using them at all. So that's the situation. What we are doing now, strategic projects. Thank you very much, Mari, for showing actually the precise projects. We have the remaps of the LKB project. Extraction and processing potentially is a big one. Let's see, it's very ambitious, a large volume, a bit lower concentration. We have a very promising project Kermac on processing and recycling in France. This is actually the elite project for recovery of heavy rares, especially for magnets. Then we have the Meka Mkangov in Poland for also long loop recycling. We have the short loop recycling Mag factory in France, and it's not only recycling, but it's also production of magnets directly, which is quite rare. And we have the recycling project in Italy, so that's very, very good. With these projects, we may change something in the EU. That's if they will materialize, it will be good. It will be good for Europe. Our benchmarks would move quite rapidly up, so which would be great. But let's see. Some of them are most of them are at pilot stages, so the full production capacity is far away yet. And I forgot to mention that we did not publish yet the non-EU strategic projects. There were some delays in acceptance by some governments, so we are coming in the next. I would not say months, but it will be decided by our commissioner, by our vice president Séjourné. On recycling, so that's the situation practically with the strategic raw materials. You see, except for copper, tungsten, aluminium, cobalt, not for battery material, not for batteries, but for steel, also nickel, is relatively fine, but again, not battery quality, battery materials quality. So that's the problem. Everything else is close to zero. So going from those zeros up to 25%, that's even for a planned economy, it would be a challenge, which we are not. So what we are doing, and we are trying to help recyclers, and we learned that this is probably the most important action, is the labeling of magnets in the products. We will try to do maximum by this year. We work with the colleagues from Joint Research Center in the European Commission. We are collaborating closely with the Standardization Committee, Technical Committee 472 on rare earths. So that could really help recyclers to identify the magnets which contain rare earths. This is very important. We will have also some. We will have stakeholders workshops beginning somewhere in the beginning of July to start the stakeholders consultation as well. Second, we have article on recycled content of permanent magnets. At the moment, we are just trying to do the calculation and verification rules. So it's we are working on that, and then maybe 2030 onwards, we may put some obligations on recycled content in products, but this is far away from now. At the moment, we need to establish what is the recycled content. At the moment, nobody knows how to actually calculate. So you mentioned that Apple would like to have 100% of recycled magnets in their thing, but how they will actually measure that? Because at the moment, there is no methodology for that. As I mentioned, we finance a lot in raw materials area. We spent many tens of millions in supporting production of rare earths and magnets, recycling, substitution. As you see, the first block of 10 projects is directly financed by us. We also finance EIT raw materials, which has targeted calls, and they also finance several projects, much smaller projects on rare earths and magnets. No time for going in detail, but that's something which you can see in the slides later. We also published the call. The call is not yet open. It will be officially open only next week, but it's pre-published, so we can say that we will have topics on recycling of end-of-life products. So that's one important thing. These are topics around 20-30 million euro. We have another topic specifically on production technologies, mining, extraction, potentially something else with strategic partners across the globe, which we have, so the strategic partnerships. And we will have one topic which is a little bit outside of this domain, but we had one topic before, 1 year or 2 years ago, on permanent magnets. Now we will focus on semiconductor raw materials. And we are funding the member states, huge funding, overall 90 million over the horizon, to co-fund their partnership. So there will be a lot of national funding sponsored by the Commission on raw materials coming in the next years. I mentioned standardization. There is one ISO committee 298 on the rare earths. Actually, it goes also a little bit to magnets. And then we created in the EU the Mirror Committee 472. China is controlling the committee, ISO committee, in a way that price is the main criterion, which is not ideal for the EU. So 472 focuses on non-price criteria as well. And that's why this work, and they have the working group on labeling, so they are supporting the Commission on the provisions of the Critical Raw Materials Act. So that's very important to see. There is another ISO committee program, is the project committee 348, established recently by Germany, and it's on sustainable raw materials, just that you know, and it's for all different materials, sustainability aspect, ideally covering the whole value chain from extraction until recycling. There is some global opposition against that because there are some established mining standards. They don't want to see this one. They believe that it's a European initiative, but it's not the case. It's really something which is neutral, and we would like to see the sustainability part in the raw materials production. So that's very important to highlight. It's quite an important new work started. On risk monitoring, just to announce, we will start next criticality round of criticality assessment in the next semester. So, and we will publish the new list of critical raw materials as the Critical Raw Materials Act says, by 24th of May 27. We will update also the foresight study, which has been mentioned several times here, and the study on critical raw materials as well. We are working also on material systems analysis, where we go in depth in the critical raw materials flows and stocks in the EU. So that's another work which we do as a package. And with member states, we started to work on stress testing. That's something very, very interesting to see. And as you see, we don't have to even stress test sometimes because China and United States are causing a lot of stress already to our economy. So some main takeaways for us, from my side, it's very important to mobilize the community of raw materials in different value chains, and especially rare earths and magnets, because that's something which is a strategic technology for the future. There are hardly any substitutes viable within the next decade. So that's too long for our industries to survive on secondary or inferior technologies. Second, we need to work on all different fronts. So I really invite community to help EIT Raw Materials, European Raw Materials Alliance, to build the network, to put industry together, to work on the standardization. Who owns standards owns the market. So that's the old message from the past. We would map facilities, expertise, equipment. We would like to put everything together. We realize now that China targeting magnets and rare earth production equipment disabled some of the new projects in the EU. So because the non-Chinese equipment is either very expensive or not available, simple. And we realized that only a couple of years ago. So that's a very interesting thing. So it's new development as well. And please support us in the implementation of the Critical Materials Act. We really try to help the community as much as we can. We try to focus and hope we see you all, and that's my last slide, on the next Raw Materials Week 2025 is the biggest Brussels event. We had last time 1,400 participants in Brussels. This time it will be from 17th to 21st of November. Main event from Tuesday to Thursday, 18 to 20. Again, with Gabriel, we are main organizers of that week. So very welcome. We will probably open the registrations around September. Thank you very much for your attention.
Yeah, thanks a lot for this overview, and it's really nice to see how active the European Commission is in dealing that problem. Before I start with the discussion, I want to do a small advertisement for the afternoon session. This morning we have seen basically supply recycling policies, but what you really can do with rare earths in terms of application, and especially where the future research is going for this unexplored family of elements will be shown this afternoon. And so stay curious. And so now I start with the discussion. Are there any questions? Yes.
If I may, thanks for this interesting session, this interesting talk. I'm an organic chemist by training, so I belong to one of these people who don't really know a lot about these lanthanoides and all these elements on the bottom. And so I was recently confronted by the statement that for electric vehicles, as we expand the market and increase our efforts in that section, those cars could potentially become more expensive. Usually when you have a technology and develop it, it becomes cheaper. But in fact, it could become more expensive because we're limited by the materials production. So is that statement, is that valid? What's your response to that? Does that make sense?
I can say something. Well, the trend, the occurring trend is exactly the opposite. In terms of rare earth elements, for electric cars, the only real problem is about the engine. Okay, there are some companies are not very open to declare what they put in their engines, but well, there are some hundreds of grams up to a few kilograms in the case of engines with permanent magnets, which are about 80% of the market. Now there is a lot of work in trying to reduce the amount of rare earth in permanent magnets and to use different types of motors. There are at least 4 competitors for that. Still, they are the most efficient. So the majority is of that kind. There are no rare earth elements in lithium-ion batteries. I want to highlight that. In some type of batteries for hybrid cars, there are lanthanides, particularly lanthanum itself. Well, I think this is not a very well-founded sentence and statement, because I mean the trend are clearly going in the other direction, and there are, as we have seen from this morning talks, that there are no risk of in principle of scarcity of these elements. The problem is only technological, political, geopolitical, whatever. But this is true for many other technologies. I mean, there are analogous rumors about the difficulties to expand and to reinforce the electric grid due to scarcity of materials. We have been expanding the grid and updating it and upgrading it over many years without any problems. So I would not pay too much attention to this alert because at present they are not funded. Clearly, there can be some raw material unavailability at a given moment for some geopolitical reasons, but we have been under this situation for 8 years with oil and gas, and we are still there, and nobody cares apparently because somebody wants to stick to oil and gas, even in Europe. So it's complicated, and I would stay relaxed, and I'm sure that also in light of what the European Commission is doing, we will have a brighter future on that than gloom time. Okay, thank you.
Are there further questions? Oh, yeah. Sorry.
Yeah, I have 2 questions. First for Maria Milan. You mentioned recycling of the magnets is a problem in consumer products because only a small part is. But I would think for those big wind turbines, we have 300, 500 kilograms of magnets. That should be quite easy to recycle. Because it's local, you know where it is, you take it out.
Yeah, that's a really good point. In the end, it's also about like the lifetime of like such wind turbines, which are not currently available on the market because they're being built. So it's more than looking at the long-term recycling. This is very interesting. But like nowadays, what's available is then consumer products with all these dismantling challenges. So in the long term, eventually, once the whole recycling supply chain is established, then there will be secondary sources that will keep on increasing, especially with
and volume-wise, that may be the major fraction. Absolutely. So recycling in the future, so maybe 2030 is too ambitious, but bright. 2040, when those wind turbines are scrapped, it may be.
Actually, you are is right. It becomes it may become a main volume or one of the main volumes. Automotive is still the driver in the volumes and will be probably in the future.
But also there, I think it's quite easy. The magnet is, it's easy. A part. You take it out.
If you identify it well, and what kind of magnet it is, that's a question. So that's why we are doing the labeling. Second, for wind turbines, technologically, there is just one thing: they are too big and they are very dangerous, and it's difficult to get them. But once you have established processes, it's possible. At the moment, there is not enough supply from.
Not yet.
Not yet, but it comes. And the recyclers, the recycling projects, most of them are counting on the supply from wind turbines. But with 20, 30 years of lifetime, first wind turbines were established not so long ago. We still have to wait.
And then my second question for Milan. You showed the production of rare earths in the EU and the strategic partners. It seems that Greenland is not part of the EU. Is that true? Because in all your pictures, it's zero from the EU.
It's not part of the EU. It's part of Denmark, but it's not part of the EU.
Okay.
And there is no production.
But Denmark is part of the EU.
Yes. But you have the same discussion with France and their territories, right? For example, Nouvelle Calédonie is the territory. At the same time, it's not part of the EU.
Okay.
Yes, we were a bit surprised as well.
Learning about the EU.
Okay, next question. Yeah.
I have also a question to Mr. Grohl. You mentioned the magnet production and also China and their prices. So I think it's not really a level playing field. So they are dominating prices, keeping it low. And we as Europeans, we need to compete with these prices when we want to produce something like here. And if we want to set something up, so how can we really compete, sir? How can we do it so that all these startups and all these projects have a chance to survive, which we will need to have by the year 2030, actually. And so what I see is I'm working at a research institute, but we are dealing pretty much also with our customers, which are from industry. And most likely they're telling us that they are not willing to pay extra if it's from Europe, at least right now. And I think it's a pretty much problem because the magnet market is quite small. However, the products, the mobility markets, the wind energy market, etc., is very huge. So situation at the moment is nobody wants to pay the extra price. How can we deal with that?
Well, that's the whole act about, right? So it's unfortunately there is no budget attached to the Critical Raw Materials Act. That was a little bit the drawback of that. But it may change in the next financial period of the EU budget. So it's multi-annual financial framework. So these next whatever 7 years could be after 27, where we think about proper funding. At the moment, there is no funding except for Horizon, which can subsidize some R&D activities. But for us, for investing in production projects, like we have only practically Innovation Fund, but the Innovation Fund is focused on decarbonization. So competitiveness is not part of the assessment, but still it's possible to apply there. And we announced already that maybe for the future it would be good to consider something like competitiveness funds or something which would help our industry to become again competitive. So not only at the beginning, that's one. Second, we are working very closely with EIB, European Investment Bank, on investment and financing the projects. We are working with other partners as well to invest, and as you've seen, in some cases, foreign investor or the like-minded countries come and invest in our projects and invest not only in capex but also in operational costs, which is quite interesting, and keep them above the water level. That's one thing. Second issue which we will have to solve, and that's the big issue, and it's also an answer about scarcity of materials, and particularly rare earths or magnets. They are too cheap. China is not counting in their price the externalities. So environmental social impacts are not counted in the price, whereas in the EU they are. So that's the issue. That's one side. Second thing is the energy prices. For that reason, in the EU we have one critical step which nobody mentioned. Oh, I think it was mentioned in one slide. We are missing. We can mine. It's close actually, because in Sweden it's possible to do that. They actually have already concentrates which they could use potentially in Kiruna. Second, we will have a lot of processing and refining capacity, but then we will ship everything to China or to UK to a small production to do metal out of that. So metallization part is completely missing in the EU. At the moment, there is no step. Why? Like for all metallurgy industry, is a question of price of energy. So that's the thing. So that's something which has to be sorted out. And we work on that also in different, not only for rare earths, magnets, but also for other metals. At the same time, we will try to see how to make the energy more affordable for the industry. Otherwise, we will not have the production in the EU. These are actually production of rare earths and magnets is an energy-intensive process. Okay, so it's part of energy-intensive industries, even if people don't name it like that. Everybody thinks it's critical raw materials only, but it's part of this energy-intensive thing. So we are working on that front as well. I must also tell you that some of the projects, again, I'm not allowed to tell it, but will be price competitive. So against Chinese already. So there are some technologies but these are really top technologies which could compete. But that's something which is where is the difference? China invested for 40 years heavily in rare earths and magnets development, and we started 10 years ago. We are far behind in R&D, but we have some hotspots in the EU which are top, or in Europe, if I can take Switzerland as well.
Okay, thank you a lot for that. I hand it over to Mario.
Nicola was.
Oh, excuse me.
Oh, please go ahead.
Maybe just a follow-up question to your remark, Milan. Your assessment, very careful assessment, it's based on established markets. Permanent magnets, neodymium were developed in the 80s, actually in US and Japan, and it's now dominated by Asia by several reasons, not only price, also technology availability. In your assessment, do you dare also to look into the future? Do you see emerging markets where Europe could take opportunity to determine the price or to determine the markets or to establish new markets? Or is this not part of the assessment?
Thank you for this question. We are actually doing foresight for strategic technologies and strategic raw materials. We are doing that, but we are not focusing on the new markets. We are identifying the technologies which are important for new era of digitalization, greening, aerospace and defense. So these are the new markets for us, and we will see, and we are trying with colleagues from German Research Center to see which technologies or which markets will be there. But we are not doing our positioning at the markets. Honestly, in most of these areas, Europe is nowhere at the beginning, the value chain. We are quite fine with certain parts of the value chain, but otherwise everything is red for us. So we are really decades behind China in many aspects.
We have a little bit time pressure.
Just one question about the recycling paradox, which is appearing now in batteries. In batteries, industry is trying to replace cobalt for price reasons, for social reasons, and we know that. But then we move towards lithium iron phosphate. But this type of batteries is much less interesting for recycling because people don't care about recycling iron and phosphorus and partly also lithium. So can the regulator, the legislator, force or promote the recycling even though we are moving towards a less intensive use of rare earth for economic reasons, strategic reasons? Because the same paradox can appear. So the less we use rare earth, the less interesting for recycling can be the items that we make. So how can we handle with this paradox?
Yes, I think the question was for you, but this is already happening, this paradox, because, for example, earth elements, there were really high concentrations in compact fluorescent lamps, which are now being phased out, replaced by LEDs, which are more energy efficient, but contain much less rare earth elements, and then the recycling is actually not worthwhile anymore. So there were existing plants doing that, which had to close again because it wasn't worthwhile. So it's already happening, and I think it's really interesting if regulations can go that way as well.
If I may just comment on that, actually this case happened already with Boliden in the past. You know, there's a mining company in Sweden, but actually is one of the biggest recyclers, and they built a huge recycling plant for electronics. And they counted, especially for mobile phones, they counted that they will recover some metals. In a few years' time, the technology changed, and mobiles are full of plastics, so it's not so worth to recycle anymore. So you see. In rare earths, we started with, I think, I must say, it was not a very beneficial decision by the Commission or by the Union to move to substitution first of rare earths because we destroyed the market on our side. As we've seen later, rare earths are everywhere, and we needed to build the market and use of the rare earths everywhere. That's exactly what Chinese did. And normally, where you place rare earths, you have the most performing technologies because they have very specific properties. And that's why Chinese are winning on all fronts because they are using material which is excellent and it's everywhere. And instead, we started with the substitution. That was these were the first steps in the EU to start with the substitution, R&D on substitution. So opposite, create market for that, apply it in the technologies. It's everywhere. We have capacity to do that. There are plenty of deposits in the EU. There is a lot of end-of-life material products coming to the EU or built in the EU, which can be recycled. So that could work. And in the Act, we have this recycled content provision potentially. So if we put after 2030 obligation to have certain amount of recycled content, this could automatically promote recycling.
Okay, thanks a lot. Due to time constraints, I would like to finish this discussion. We have still some science in the afternoon. I thank all participants, all speakers, and with that, I hand over to Annalisa Corrado.
Yes, thank you very much indeed. It's been a really interesting panel with really high-level speakers, and it shows exactly how complexity looks like. So also for policymakers that have to build paths when the things are changing with a very high speed, and so it's really difficult to do, and it's why that is why I think we have to stay together, stay in touch, and scientific, technological innovation, policy making should go hand in hand, and it's crucial. And I would like only to point some things that we heard: long-term benefits more than short-term interests, and this is for the politician side. It's crucial for us, I think. And then another thing that is really important is that for everything we listen, I think that multilateralism and cooperation it's crucial, and is a geopolitical matter, and it's really incredible how at the end of our discussion, it's clear that we have a huge problem with energy, but to lower the price of energy, we need renewables. But if we need renewables, we need, yes, and so it is not only circular economy, but also a circular problem. And so to solve it, we really need our best and creative ideas, no? And so also because it cross also other issues as like border adjustment mechanism, taxation systems, and also the problem of the externalities in the price composition that made primary resources lower in costs from secondary resources. That is the problem we have, and we face not only in the rare elements but also in a lot of products here in Europe. And so also I like the reference to from the announcement to reality. There is a huge street to build and to do, and so. Also because we have some business cases that in a few years becomes old, and so as Europe we also have to plan strategically where, how, and who, and trying to not kill new projects, but to boost the cooperation. And every time I face and I have the opportunity to go deeper in details in one sector, I urge that European institutions should be really stronger to build also strategic plans, industrial plans, energy plans together, and not only like member countries. And this is obviously a political opinion, but I think it's important. So I'm sorry that the time is finished, because it is a really important discussion, but we will keep in touch, and we have the presentation that should be studied, because every presentation was full of really interesting information. And so thank you very much indeed, and we will see you soon, I'm sure. Thank you.